Let ABC be a triangle with AB equals 7, BC equals 8, and CA equals 9. Let omega be its incircle, and suppose omega meets sides BC, CA, and AB at D, E, and F respectively. Let AD meet omega at D and P. The circle passing through A and P tangent to omega meets the circle passing through A and D tangent to omega at points A and K. Then KF over KE can be expressed as M over N, where M and N are relatively prime positive integers. What is M plus N? This is triangle ABC, which has side lengths 7, 8, and 9, and incircle omega, which intersects sides BC, CA, and AB at D, E, and F respectively. Then we're going to draw in line segment AD. And that line segment would have met omega earlier at P. We're given the circle passing through A and P tangent to omega, which is this circle here. And then another circle passing through A and D tangent to omega, which is this circle. And that intersects the circle I described earlier at points A and K. And the second point, K, we want to find what is KF over KE. First off, we see we have three circles, which are namely omega, the circle tangent to omega at point D, which I'll call omega 1, and the circle tangent at point P, which I'll call omega 2. And we know the places where all three of these circles intersect. So we can draw each pair of circles' radical axis, which shouldn't be too hard to figure out based on the points where they intersect. So circles omega 1 and omega 2 intersect at points A and K, so the radical axis is line AK. Now circles omega and omega 1 are tangent at point D, so their radical axis would be the common tangent at point D, which is just line BC, because the incircle tangent at point D is just line BC. And then circles omega and omega 2, their radical axis is their common internal tangent, which passes through point P, like this. And these three lines will all concur at a single point known as the radical center. There we go, let's call it X. Now, you might be thinking X, maybe it also lies on line EF, but to see whether that's actually true, we have to go to cyclic quadrilateral DEPF. Then from the perspective of cyclic quadrilateral DEPF, X is simply the intersection of the tangents to its circumcircle, which is omega at D and P. The tangents to omega at D and P intersect at X. But quadrilateral DEPF has a very special property, and that is that the tangents at E and F intersect at A. And A lies on line DP. The tangents to the circumcircle of this quadrilateral at two opposite points meet on the line formed by connecting the other 2 points. And that's always true. So we can apply it to the other set of points as well. We can say that the tangents at D and P will also meet on line EF. And the tangents at D and P meet at X. So X lies on line EF. There we go, we found that X lies on line EF. So we can now make some power of a point observations. We know that XD squared equals XE times XF, which is equal to XP squared. But that's also the power of X with respect to circle omega 2, which is also equal to XA times XK. So we see that XE times XF equals XA times XK, which brings us to conclude that quadrilateral AKFE is cyclic. So now we know that quadrilateral AKFE is cyclic, and I've drawn the circle that passes through those 4 points. And that can allow us to find some equal angles and similar triangles, especially if we use point X, that can then allow us to determine the value of KF over KE. So let's start with angle XKF. As you can see in this diagram, that's equal to pi minus angle FKA, which is equal to angle FEA from the cyclic quadrilateral. And that's equal to angle XEA. We also have angle XKE, and that's equal to pi minus angle AKE, which is equal to pi minus angle AFE. That's equal to angle AKE because of the cyclic quadrilateral, which is simply equal to angle XFA. So we have that angle XKF is equal to angle XEA, but also angle FXK is equal to angle AXE. So the two triangles XKF and XEA are similar. We can write that down. Triangle XKF is similar to triangle XEA. And from the second one, we also have a similar thing that goes on in the second equation. We have that angle KXE equals angle FXA. So these two triangles, that makes them similar. We have XKE is similar to triangle XFA. So we can get some similar triangles relationships from these two triangle similarities that can possibly allow us to find KF over KE. So we have XK over KF equals XE over AE. And from the second one, we have XK over KE equals XF over AF. From here, we can find KF over KE. And KF over KE is the same thing as if you do KF over XK times XK over KE. And that's equal to the reciprocal of the first fraction, AE over XE, times XK over KE, which is XF over AF. But if you notice, AE equals AF, because they're both tangents to omega at A. So if we can cancel them out, we're left with XF over XE. So all that remains is to find XF over XE, and then we're done. So we want to find XF over XE, and we can do that using Menelaus's theorem. If we have a triangle, AFE, and a transversal that passes through X. And the only one that doesn't pass through AF or E here is XBC. So we use it on triangle AFE with transversal XBC. And so we get AB over BF times FX over XE, which is exactly what we wanted, times EC over CA equals 1 by Menelaus's theorem. Now we know that AB is 7 and CA is 9. So we just have 7 over BF times XF over XE, which is what we want. I'll just call that little x, times EC over 9 equals 1. Now BF and EC are tangents at B and C to the incircle omega. And they simply have lengths S minus B and S minus C respectively, where S is the semiperimeter of triangle ABC. Since triangle ABC has side lengths 7, 8, and 9, S would be equal to the perimeter 24 over 2, which is 12. So 12 minus B, which is 12 minus AC, is equal to 12 minus 9, and that's 3. S minus C is 12 minus C, that's 12 minus AB, which is 12 minus 7, or 5. So we know that BF is 3 and CE is 5. So we have 7 over 3 times 5 over 9 times x equals 1. So x equals 3 times 9 over 7 times 5, and that's equal to 27 over 35. It can be expressed as m over n, where m and n are relatively prime positive integers, What is m plus n? 27 plus 35 is equal to 62. And we are done. Thank you for watching my YouTube video, and please follow my channel if you would like to see more videos.